before we get into this. All right, it's 8:30. Let's go and get started. Good morning, everyone. How's everyone doing today? Doing good. So second day after spring break, so hopefully everyone's getting back into the swing of things. All right, so the plan for today is I want to finish up our lecture notes on Fourier series, and so after today you should be able to do everything on homework 5. I remember homework 5 is due, I believe, next Wednesday. So Wednesday at 11:59 p.m. So you guys have about a week more to do it. And after today, you should be able to do homework. All right. About it. Not that many announcements today. Are there any questions I can answer before we get started for today? Okay. All right. Let's just jump right into it then. Okay. So we left off on Tuesday talking about this idea of a Fourier series expansion. The idea with the Fourier series expansion is that it's almost like a transformation. Maybe transformation is not the right word for it at this point. And so next week we'll actually go over the Fourier transform and what that actually looks like. But when we talk about a Fourier series expansion, maybe a better way to say is that it's a different function representation. Okay. And so if I were to sum up the definition of a Fourier series expansion, is that I would say that if you have a periodic function f of t, and the emphasis there is on periodic, and so it has to be a function that repeats itself. What the Fourier series expansion says is that we can take that periodic function and represent it as an infinite sum of sine and cosine terms. And so the formula that we have is f of t is equal to a naught, which is a constant. We'll talk more about the constant term today because that term has some significance. But the main part of the Fourier series expansion is this. So we have a summation starting at n is equal to 1 up into infinity. An cosine of nt plus bn sine of n. Okay. You could take any periodic function and represent it in this form. Okay. And this form, you might be wondering, if we have f of t already, what's the purpose of kind of representing it as this kind of very complicated form? Because it kind of seems like we're making it worse. Well, when you represent it as this form, you kind of learn a lot of interesting information about the function, mostly about how the different frequencies correlate with that function. Okay. And so when I say that, or when someone says to compute the Fourier series expansion, what you're actually computing are these right here. Okay. And so that was the example that we did at the end of class on Tuesday. So we took a periodic function and we computed expressions for those coefficients. Remember from last time, we had three formulas, one for A0, one for AN, and one for BN. And we used those formulas to compute, what these coefficients are. Okay? And believe it or not, those coefficients actually tell you a lot of valuable information about a function. Okay? And so whenever we're computing Fourier series, that's essentially what we're doing, computing, what these coefficients are. Okay. So we'll get back to that in a second. So we'll definitely do more examples today of how to compute those coefficients. But I wanted to start today about, talking about this idea of truncation. In particular, one thing that should stand out to you about this formula here is the fact that this summation is infinite. Okay. That means in theory, you have to keep adding an infinite number of Fourier terms in order to fully realize the expansion. Okay. So let's start by saying strict. So the strict definition, that if you want to go straight by the books, by the from based on that equation above, in order to fully realize your Fourier series expansion, it has to be an infinite summation. Okay. But in reality, an infinite summation is not really practical, and so we saw that in our example last time, right? So even though we did all that work to compute the coefficients, we only really had the the energy or the effort to write down three of the coefficients, right? And so practically speaking, you're not going to be writing down an infinite number of coefficients. That's really not practical. Okay. And so practically speaking, when you do, I would say kind of a practical Fourier series, you cut this off at a certain point. And so you don't actually add an infinite number of terms, you add a finite number of terms. Okay. And so now our expression looks like this. Okay. So we have f of t. Instead of an equal sign, so now that we're essentially cutting off some terms, we're not adding an infinite sum, we're not going to have a straight up equal sign anymore. Okay, so I'm going to have a squiggly equal sign instead. Okay. So this squiggly equal sign basically means approximately equal to. Okay. It's going to be equal to A naught plus, we still have a summation, but instead of being infinite, we're going to cut this off at a certain number. And so I'm going to say that number, is going to be big N. Okay. The rest still stays the same. So an cosine nt plus bn sine. Okay. For now, the big difference here is this n right here. Okay. So this is some finite number. So be like 5, 6, 7. Traditionally, when I've used Fourier series in my own work, I usually cut it off at 10. So 10 is usually a pretty good number for most functions. So it's something other than infinite. And so when we do this, when we cut off the Fourier series and we don't add it up to infinity, we call this truncation. So we're basically truncating the Fourier series version. It's truncated because we're not including all the terms that are out there. Okay. So truncation is something that happens, a lot, especially in a lot of applications that use Fourier series. And so if you remember from the end of lecture on Tuesday, I talked a little bit about, audio compression, right? And so if you work in kind of audio engineering, a big part of that field is how to compress sounds into, a finite flat size, right? And there's varying levels, and so depending on how high fidelity or how accurate you want your sound file to be, you can make it, as big or as small as you want. The way that kind of works, essentially, kind of at its core, is very similar to the Fourier series, okay? Or very similar to a truncated Fourier series. Because if you wanted to, if you work in audio engineering and you wanted to basically compress a music file, you want to compress a sound file down to a certain amount, essentially what you're doing is you're throwing away a lot of these higher order or higher frequency Fourier series modes. Okay. Because in reality, if you're looking at practical sound, even for a wide range of human voices, that only exists for a certain range of frequencies, right? And so in reality, you don't need to capture every single audio frequency out there. And so you only need to capture just a set amount in order to make in order for the sound to get across. Okay? And so essentially, in audio compression, we're basically throwing away a lot of that, a lot of those frequencies that just aren't practical. Of course, real audio compression, it's a lot more complicated than that. I don't want to kind of oversimplify it because, I know people that work in that field, and it's definitely a lot more than that. But it's, that's essentially kind of the idea behind it. Okay. And we can apply that same idea to Fourier series and making it practical. So generally speaking, of course, the more terms that you include in your truncation, so the higher your big M, the more accurate your theory is going to be. But it's going to take a lot more work. Okay? So you kind of have this trade-off of work versus accuracy. Okay? All right, any questions on this? Okay. All right, so that's the basics of the Fourier series. Okay. Let's make it a little bit more general. And so let's talk about Fourier series expansions for a function with an arbitrary period. But so far, if you look at the example that we did last time and all the formulas that we've covered so far, one assumption that we've made is that the period for the function is 2 pi. Okay, and so that's great. And so and there's some proofs that you can use or you can see, which shows that if your period is 2 pi, then the Fourier series is going to converge very easily. But in reality, there's a lot more functions out there that have periods that are not 2 pi. So, the question is, can we extend the Fourier series to these functions that, have an arbitrary period? And so it can't be just be 2 pi, so maybe it's 3 or 4 or just whatever frequency is out there. Okay. And of course the answer is yes, otherwise I would not bring this up. Okay. And so the only thing is we have to modify our equations as well. Okay. And so our formulas here are going to change this just a little bit. And so, let's go ahead and write them. Okay. And so for an arbitrary period, and so let's say that our period here is 2L. Which is kind of a weird way to express the period, but basically, this variable L, that L is considered the half period. So whatever your actual period is, or whatever amount of time it takes for your function to repeat, just cut that in half, and that's your variable L. Okay, and so for that, our Fourier series expansion looks like the following. So we still have A naught, and so A0 is still there. Okay. We're still going to have our infinite summation. So right now I'm just doing kind of the explicit definition for this. So it still has the infinite sum, but all the same rules about truncation still apply to this one as well. Okay. We're gonna have an sign. Here's where the changes occurs. And so instead of just nt, we have n pi t divided by L plus bn sine n pi t L. So the argument inside the sine and cosine changes slightly. Okay, to adjust for the fact that our period is not 2 pi anymore. And now our formulas for the coefficients are going to change as well. Okay, so we have 3 formulas here. So we have A0. Okay, this can be equal to 1 divided by 2L integral minus L to L of f of dt and so a slight change there, accounting for the fact that our period is pretty different. Our formula for AN looks like the following. So we have 1 over L integral of minus L f of t cosine of n pi t over L dt and finally bn looks very similar. So you have 1 L integral from minus L to L f of t sine of n pi t L And actually, if you had a period of 2 pi and you apply these formulas, you get the same formulas as we had before. So, this is one of those rare cases where these formulas here are kind of now the master formulas. And so you can, we used the formulas last time just because they were a little bit simpler, because it was our first time doing Fourier series, but these are the ones that you would just kind of use in practice. Okay, and so next we're going to apply this to an example. But before we do an example, are there any questions on this? Okay, all right, so let's do an example. Let's see how this is actually used in practice. Okay, so let's find the Fourier series expansion for the following functions. And so we have f of t, and I'm going to represent it as a discontinuous function. So we have three different zones here. And so the first zone, f of t is going to be 0. This is going to be from -2, which is less than t, less than -1. Okay. Let's say f of t here is equal to 7, or -1, which is less than t, less than 1. And then it's going to be 0 again from 1, less than t, less than 2. Okay. So visually, the function looks like this. And so if we start at -2, we go to +2, we mark off -1 and 1 as well. So that's -1, 1. Okay. And so from -2 to -1, we know the function has a value of 0. Okay. Then starting at -1, the function is going to jump up to a value of 7. Okay. And it's going to continue like that until t is equal to 1. And from there, the function is going to go down again and go back down to 0. Okay. And so we have basically like a square pulse. Okay. And then this function here, the assumption is that it's going to repeat. So we're going to go over here a little bit. So this is kind of the cutoff right here. And then up again. Just like that. Same thing over here. Cutoff. Basically like that. We have kind of a square pulse that's going to going up and down. All right. So first thing I want to identify here, and first thing that you should do in these problems is you want to identify the period. Okay. So how long it takes for this function to kind of repeat. Okay. Okay. So based on this function representation, we can see that our function here starts at t is equal to -2. Okay. And then it ends at t is equal to 2. And so if we measure the amount of time between -2 and 2, that is 4 seconds, basically. So our period here is 4 seconds. Okay. And so if our period is 4 seconds, that means our value for L being the half period, is just 4 divided by 2. So L here is 2. 2 seconds. Okay. So let's use that information to solve for the coefficients. Okay. And so remember, when a problem asks you to solve for the Fourier series expansion, it's basically asking you to compute the values for A0, AN, and BN. Okay, so you have basically 3 computations that you have. All right, before we start that, are there any questions on this? Okay. All right, so let's go ahead and plug in. Let's start with A0. Okay, so A0, our formula for this is 1 divided by 2L integral minus L to L of f of t dt. Okay. And so let's go ahead and plug in our function. So our L value here is 4. We're going to have 1 over 4 integral -2 to 2 of f of t dt. Okay. And so all I did there was I just plugged in the value for L into our integration. Okay. And so once again here, just like the example we did last time, we have a discontinuous function where the function is 0 for a significant part of this. Okay. And so for the parts of the function where it's 0, we're not going to integrate those parts because it's just function 0. Okay. So I'm only going to focus on the parts of the function that are non-zero, which is between -1 and 1. Okay. And so this integral, it simplifies to 1 over 4 integral from -1 to 1 of 7 d. And so the key here is that, the integration bounds change. So instead of being -2 to 2, I change it from -1 to 1. Because between -2 and -1, the function 0, and between 1 and 2, the function is 0 as well. So we're just going to ignore those parts. And so in the middle there, our function value is 7. Okay. And so this integral here is very easy to compute. And so we have 1/4 times 7. 7 is just a constant, and so we have 7t evaluated from -1 to 1. Okay. And so this is going to be 7/4 times 1 minus -1. And so that 1 minus -1 here is going to be equal to 2. This 2 is going to cancel out with this denominator. And so what we get is A0 is equal to 7/2. All right. That's A0. Let's go ahead and compute AN now. And so our formula for AM is 1/L rho minus L of f of t cosine of t L. All right. So once again, we're going to do the same thing we did for A0. We're going to plug in for the value of L, but we're also going to simplify this and only integrate over the parts where the function is non-zero. Okay. So our L value here is 2. So we have 1/2 integral. Right. The function is only non-zero between -1 and 1. Our f of t during that time is 7. We have cosine of n pi t divided by 2 d. All right, and so what we can do from here is we can take 7, we can factor it out because it's just a constant, and then we just have an integral of a cosine function, which is fairly simple. Okay. Okay, so let's go ahead and do that. So let's take the 7, let's bring it out in front. We have 7/2. Okay. Integral of cosine n pi t over 2. So that's going to be, we're going to take the reverse chain rule. So you have 2/n pi times sine of n pi t over 2. We're going to evaluate this from -1 to 1. Okay. All right, so let's go ahead and simplify this. And so the 2's out in front are going to cancel out. And so we have a 7 n pi times sine of n pi divided by 2 minus sine of minus n pi. I'm just plugging in 1 and -1 in for t. And so that's that gives us that function there. All right. So we can simplify this. If you remember from class on Tuesday, I brought up this idea that functions can be even or odd, right? And so we looked at an even function last time. And so for an even function, when you have a negative argument in there, then it ends up just kind of going away, right? So for even functions, this is going to be inside right here. And so for even functions, if you have f of minus t, for instance, okay, that's just equal to f of t. And so that minus argument kind of goes away. So the classic example of an even function is cosine. So you have minus cosine of minus t. This is equal to cosine of t. Okay. That's because for even functions, the function is the same on both sides of the y-axis. So that's why we can kind of make that simplification. Okay. And so if we have even functions, then we also have odd functions. But odd functions work in a very interesting way. And so let's say that we have a function f and we're plugging in minus t into an odd function. Okay. If your function is odd, what you can say is that you can bring that negative, you can take that negative and bring it out in front. It ends up as minus f of t. The classic example of an odd function is sine, right? And so if you have sine of t, or I should say sine of minus t, okay. What this is equal to is minus sine. Okay, so we can bring that minus sign out in front of this. Okay. So why am I bringing this up? Why am I bringing up even and odd functions? It's kind of a weird aside here. Okay? Well, in our solution so far, we have a function that looks exactly like that, right? So we have sine of n pi t over 2, and we have a sine of minus n pi t over 2. Okay? But since we know that sine is an odd function, okay? Since sine of it is an odd function, what we can say is that sine of minus n pi t over 2, okay, this is going to be equal to minus sine of n pi t over 2. Okay? We can bring the negative out in front. And so that's nice because now we have two sine functions with the exact same argument. Okay? And because we brought the negative in front, this negative right here that came from the odd function is going to cancel out with this negative right here that came from integration. So we actually have an addition of these two terms. Okay. And so if we put it all together, our expression for an is going to be equal to 7 n pi times 2 sine of n pi t over 2 . And of course, the 2 can multiply out in front as well. And so this can be 7 times 2 is 14. 14 over n pi sine of n pi . So that is our result. Any questions on how we got this result here? Okay. Right, so we're looking good. So we have A0, we have AN. Okay. Let's simplify this a little bit because we have that sine of n pi over 2. Okay. Remember last time we talked about what to do when you have cosine of n pi, sine of n pi. This one's a little bit different because we have sine of n pi over 2. So let's see what this expression looks like when you plug in various values of n. that's essentially what we're going to be doing when we plug this back into our Fourier series expansion. So let's plug in n is equal to 1. And in fact, I'll group all these together. Let's say n is an odd number. So n is equal to 1, 3, 5, 7, 9, 11, 13. You know the odd numbers. So let's look at sine of n pi over 2. That's sine of pi over 2. Okay. Here's sine of 3 pi over 2. Sine of 5 pi over 2. Dot, dot, dot. Okay. So this continues on forever. Okay. What is sine of pi over 2? So sine of pi over 2 is 1, right? Sine of 3 pi over 2 is just minus 1. Okay. Sine of 5 pi over 2, you can see, you know, that's after you make a full rotation, and then you come back up to the y-axis again. And so this is equal to 1. Okay. And so hopefully you're starting to see the pattern. And so when n is odd, then we're basically alternating between 1 and minus 1. 1 minus 1, 1 minus 1. Okay. We have kind of the same deal as we did before, just slightly changed because we have the divide by 2. Okay. Let's look and see what happens when n is even. N is equal to 2, 4, 6, 8, 10, 12. Write a couple of these. So when n is equal to 2, we have sine of pi. When n is equal to 4, we have sine of 2 pi, sine of 3 pi, so on and so forth. Okay. Okay. What is sine of pi? Sine of pi is just 0, right? Sine of 2 pi, also 0. Sine of 3 pi, also 0. Okay. So what does this tell us? And so this tells us that when n is even, then an is equal to 0. Okay. And when n is odd, you know, you have to make sure that you choose the sign appropriately according to that value of n. Okay. So the thing with Fourier series, and the reason I'm kind of bringing this up is that a lot of it is kind of like pattern recognition almost, right? And so you have a lot of these sine and cosine terms with pi's and n's in there. And so kind of, you know, the better you are at kind of seeing these patterns and kind of seeing what that looks like, it ends up, you know, helping you a lot. And it kind of comes out in the solution. Okay, and so we'll see this again, you know, once we write out the full expansion, but you know, I just wanted to make you aware of it. Okay. All right, so that's A0, we have AN. Let's go ahead and write our expression for BN. Okay, so BN, our formula for this is 1 over L integral minus L to L T sine of n pi t for L dt. All right, I'm going to go ahead and plug in for everything. And so we have our value of L, which is equal to 2. Our f of t is 7. Okay. And so this integral becomes 7 over 2 integral from minus 1 to 1 of sine n pi t over 2 dt. All right, so let's go ahead and perform this integration really quickly. So we have a 7 over 2. Okay, we integrate sine. We end up with a minus 2 n pi sine of n pi t, n pi t divided by 2, evaluated from -1 to 1. All right. We have these 2's are going to cancel out. And so what we have here is a -7 pi times cosine of n pi over 2 minus cosine of negative n pi 2. All right, so let's go ahead and invoke our even and odd function. And so what we have here is cosine of minus n pi over 2. And so because cosine is even, this is equal to okay. So since cosine is even, we're just going to negate the negative, and so this is going to be cosine of n pi over 2. Okay. Okay. And if you have a cosine of n pi over 2 minus a cosine n pi over 2, okay, we have two exact functions. They're going to subtract each other. They're just going to cancel out. Okay. And then what we get in the end is bn is just equal to 0. Okay. All right, so that simplifies things for us. So we don't have to worry about bn here. Okay. And so we can just work with a0 and an. Okay. So now that we have the coefficients solved for, we have a0, an, and bn. Now we can plug these back into our Fourier series expansion. Okay, so Fourier series expansion, we have f of t is equal to a0 plus infinite summation, which we're not going to do infinite, we're going to cut it off at a certain point, an cosine of n pi t divided by 2 plus bn sine n pi t 2. Okay, bn is equal to 0 here, and so we're not going to worry about that. Okay. And so for all values of n, that bn is equal to 0, so we're not going to worry about that part. So we're only going to worry about a0 and an. So let's go ahead and plug it in. So our a0, if you remember, like 15 minutes ago, our value for a0 was 7 over 2. Okay. And then our expression for an was 14 over n pi, sine of n pi over sine of n pi over 2. Let me go ahead and write that. So and here is 14 pi. Okay, so let's go ahead and plug in various values for n. So let's start with n is equal to 1. And so when n is equal to 1, we have 14 over pi. Okay. We have sine of n pi over 2. So n here is 1. So sine of pi over 2 is just positive 1. Okay, so our sign is correct. So that's the coefficient, and then we have to multiply it by cosine of pi t divided by 2. Okay. So this 14 over pi, this came from an. Okay, so that was the contribution from an. And this cosine of pi t over 2, that came from the expansion. Okay. So when you're writing these function expansions down, it's a little bit easy because there's a ton of sines and cosines kind of floating around. So, make sure you kind of are, you kind of do this part a little bit carefully because it can be very easy to get confused. Okay. So that's the n is equal to 1 term. Now let's add the n is equal to 2 term. But we know that for n is equal to 2, an is equal to 0, right? So we know a2 is equal to 0. So we're not going to write this term. I'm just going to put a 0. You don't have to write a 0. You can, in reality, you can just leave it off, and then everyone will kind of understand that. But because this is only our second example, so I want to make sure that that part's clear. Okay, so now let's write our n is equal to 3 term, and then we'll just kind of stop it from. All right, so for n is equal to 3, our coefficient is, so a3 is equal to 14 over 3 pi times sine of 3 pi over 2 where the sine of 3 pi over 2 we know is -1. Okay, so we're going to have a minus sign out here. So you have a minus 14 over 3 pi. And then our cosine term is going to be cosine of 3 pi t divided by 2. And in reality, this summation is going to continue on. Well, we can write n is equal to 4. So we know for n is equal to 4, our coefficient is going to be 0 again. But then, for n is equal to 5, 6, 7, you can continue this for as long as you want. Usually for the homeworks and for the exams, I only ask for maybe like 3 terms. So usually if I can see 3 terms, then I can tell whether you got it. So don't write more than 3 terms for your stuff. Otherwise, it just kind of gets tedious. Okay. Any questions on this example here? Okay. All right. So we've done 2 examples so far. So we did an example at the end of class on Tuesday. We did an example right now, just on Thursday. Okay. And so I want you guys to notice something. So if you go back, you go back in your notes, and you look at the example that we did last time. We ended up with a situation where, for the example we did last Tuesday, where a0 was 0 and an was 0, but bn was not 0. Okay, so hopefully you're starting to see a pattern here where either the a's are going to be non-zero or the b's are going to be non-zero. But for the last example on Tuesday, the bn was non-zero, but the a's were 0. Okay. Let's fast forward to today. We had an example where the a's were non-zero. So a0 was non-zero, an was non-zero, okay, but bn was 0. Okay, that's not a coincidence. And so let's talk about how we can simplify some of the work that goes into doing these Fourier series expansions. Okay. Because a lot of times, unless it's kind of a weird function, you can kind of tell right away which coefficients are going to be 0. It's either going to be an or bn. It's going to be 0. Okay. And the trick that we're going to rely on here is, again, whether our function is even or odd. So this trick is important because it's going to save you a lot of work. Because if you look at the last 2 examples we did, it took us a ton of work to compute, 3 sets of coefficients, right? And so, if you can simplify that, if you can only compute 1 or 2, that's going to save you a lot. Okay. So let me start by saying this. So we can automatically assume some of the Fourier coefficients will be 0. Okay. If our starting function f of t is either even or odd. Okay. And the rules kind of go like this. So if f of t is even, then Bn is going to equal to 0. Okay. And if f of t is odd, that means a0 is equal to 0, an. Okay. Okay. So you can automatically assume this. And so, if you're doing the homework and you're working on a function that just by looking at the function is either even or odd, then you don't even have to compute the other coefficients. You don't even have to show me the work. And so you can just say that, this function is even, and so I'm only going to compute a0 and an, or this function is odd, so I'm only going to compute bn. Okay. All right, so this should save you a ton of work because, instead of computing 3 sets of coefficients, you only compute. So let's talk a little bit more about how can you tell if a function is even or odd. Okay. All right, how can you tell? And so I think the easiest way to tell, or at least the way that I initially learned it, and what kind of stuck with me throughout all these years, is to look at the function visually. Now that I've been doing this for way too long of my life, I can look at a lot of functions and tell without drawing if it's even or odd. But the way it kind of manifests in my head, the way it kind of sticks is I look at the visual representation. Look at the function visually. I plot it in my head, and I can tell from there whether it's even. Okay, so an even function. An even function will be identical if you reflect it across the vertical axis. The word I was looking for is symmetric. So an even function will be symmetric across the vertical axis. So let's look at a classic even function. Let's look at ft equal to t squared. Okay, so quadratic function. Okay, so a quadratic function looks like the following. So we have kind of this bowl parabola. Okay. Imagine I drew this better, so it actually is symmetric. Okay. And so if we were to draw, I call it a line of symmetry, but you can almost think of it like a mirror. Okay. If you drew a line of symmetry across the vertical axis, and you kind of look at the function on both sides of this mirror, they should look the same. Or it should look like a reflection across that mirror. So that's how you can tell a function is even. So you draw, or you look at the vertical axis and you try to see if it's reflective across that axis, symmetric. An odd function is a little bit more difficult to draw. But there is a line of symmetry for an odd function. And so an odd function will be symmetric across a diagonal line. Okay. And the diagonal line is just a linear function. So you can either use f of t is equal to t or f of t is equal to minus t. Okay. So let me give you an example here. So we have f of t. F of t is equal to t is actually an odd function. Okay. And so if we were to draw that, f of t is equal to t looks like this. Okay. If I were to draw a line of symmetry like this, okay, and so it's basically a diagonal line that crosses through the origin. Okay? And if you look on both sides of this line, you know, you should see a mirror reflection. Oh. And so a function is even or odd, you know, that saves you a lot of work in how you do this, how you do the expansion, because you can just compute one or the other and not have to worry about it. All right, any questions on even and odd functions here? Okay, all right, so I'm looking at the time right now. We have just about 15 minutes left. We're not quite as far today as I want to be, so I think we're gonna be finishing up this lecture on Tuesday. But I don't want to leave you guys hanging, so I don't want to have you guys wait until Tuesday to finish up the last part of the homework. So I'm going to extend the deadline for homework 5. So homework 5, I'm going to push back until next Friday, just so you have a few extra days for that. Okay. I think we'll probably end up pushing the midterm back a bit too, because we're a little bit behind schedule. But that's okay. There's a lot of extra time at the end of the semester, but you know I don't want to kind of rush through these things here, because I felt like when we did Laplace, I kind of rushed through that a little bit too much, and I think it was a little bit tough. So you know, I want to make sure I give Fourier kind of its needed time, because it is kind of an important topic, and I want to make sure that we cover it. Okay. So I'll push back homework 5. Homework 5 will be due next Friday, and then there'll be one more homework 6. So we do a week after that, and then the midterm will probably be pushed back one class session as well. Okay, so let's do one last example today. Kind of see this in action. Okay. So let's find the Fourier series expansion of f of t is equal to t. That's right. Let me write down f of t, and the period for this function is going to be 2. So we have -1 less than t, which is less than. Okay. And so this tells us here that our period is 2, and thus our value for L is going to be. Okay. So let me go ahead and draw this visually. Let me go ahead and mark off -1, 1. Okay. Okay. And so the function f of t between -1 and 1 looks like the following. Okay. We have just a linear line that goes up like that. Okay. But because this is a periodic function, once we get past t is equal to 1, then this exact pattern is going to repeat. So, it looks actually kind of cool. So once we get to 1, the function is going to repeat here. Okay, so we're going to go back down. Function. Okay. And so we end up like that. Down, that, down, and that. Okay. Just like. And so what we have right here is kind of a classic sawtooth pattern. Okay. All right, and so what we want to do is we want to find the Fourier series expansions, the Fourier series coefficients for this sawtooth wave. Okay. So before we start solving the coefficients, let's see if we can kind of simplify this process for us, right? So we have our function here. We have f of t is equal to t. Okay. What we know about f of t is equal to t is that it's an odd function, right? So you can draw the line of symmetry, and actually, we drew it up here, actually, right? And so we know just from visually and just by looking at it, this function here is odd. Okay. And so since this is odd, this saves us some work. So we know that normally we have to compute a0, an, and bn, right? We normally have to compute all 3 for a Fourier series expansion. Okay? But since this function here is odd, then that tells us that a0 and an are going to be 0. We just know that right away because the function is odd. So this is going to be 0, and that is going to be 0. Okay. And so the only one we actually have to compute here is bn. And so bn is the only one we have to compute. I'll prove it to you too. So I'll compute a0. I'm not going to do an. That one takes a little bit more time. But we'll do a0, and I will show you right away that it's 0. Okay. Okay, so let's compute a0 very quickly. So a0, our expression for this is 1/2L times integral from -L to L f of t b. Okay. Okay. Let's go ahead and plug in for this. And so we have L is equal to 1. So we have 1/2 integral from -1 to 1. Our f of t here is just t. So it's going to be t dt. Right. So we have a 1/2 out in front. Then integral of t is just going to be 1/2 t squared. Evaluated from -1 to 1. As we do this, we have a 1/4 times a 1 squared minus -1 squared. So now we put, and so now we evaluate this. -1 squared is just 1. So we have 1 minus 1 is equal to 0. Okay. So what we get is a0 is equal to 0, just like we predicted. Okay. So you can run through the calculations for AN, and it's going to give you the exact same thing. Okay, so maybe that might be something good to if you were somehow bored for a 20-minute stretch. And so, but you can trust me on this, that it's 0. And in fact, in the notes I calculated out, you should see it's 0 as well. Okay. So now that we've established the A coefficient is going to be 0, let's go ahead and compute Bn. So our formula for Bn is 1 over L integral -1 to 1 of f of t sine of n pi t divided by L dt. All right, so let's go ahead and plug in for all the variables here. So we know L is 1. L is an integral from -1 to 1. Our f of t here is just t. We have a sine of n pi t dt. All right. So we have an integral here that we're gonna have to do by parts. Okay, so we have t sine of n pi t. So let's integrate this by parts, and so we have b or u, sorry, u is equal to t. The du is just going to be equal to dt. Okay. dv here is going to be sine of n pi t, and that means v here is going to be -1 over n pi sine of n. So we do this plus sign, this minus sign, and so that means our integral for -1 to 1 of t sine of n pi t to minus t n pi cosine of t minus, so that's going to be a plus. Okay. Plus 1 over n pi integral of cosine and okay. All right, so let's go ahead and perform that last integral there. So we have a minus t over n pi cosine of n pi t, okay, plus 1 over n pi squared n pi t. And we're going to evaluate this entire expression here from -1 to, okay. All right. So let's go ahead and plug in for t. Okay, so remember, t is our integration variable. So when we're plugging in for the integration bounds, we're plugging in for t. Okay. And so let's plug in for 1 first. Okay. And so that gives us -1 n pi cosine of, okay, plus 1 over pi squared pi minus, then we have a -1 times -1 times over pi, that's +1 pi cosine of pi plus 1 over n pi squared sine minus n. All I did for that step is I just plugged in the integration back. Okay. So we can simplify this quite a bit. Okay. So there's a lot of terms here that's going to cancel out, and a lot of terms here that's going to combine together. Let's look at the sine terms first. So we have sine of n pi, sine of minus n pi. Okay. And so we know, because of the way sine is designed, right? So, and because n is integers here. So if we have n is equal to 1, we get sine of pi, sine of 2 pi, 3 pi, so forth. Okay. No matter what the value for n is, okay, this is going to be equal to 0. And this is also going to be equal to 0. That was kind of the same as kind of what we found last on Tuesday. Okay. The other thing we know is that since cosine is even, that means cosine of minus n pi is this going to be equal to cosine of n. Okay. And so that that minus sign in the argument kind of just goes away. All right. And so from this, remember what we're solving for is Bn. If we negate the sine terms and we kind of make that change for the cosine, we get minus 1 over n pi cosine n pi minus 1 over n pi sine of pi. Okay. We can just combine these together. So we get Bn is equal to minus 2 n pi cosine. That is our Bn. Okay. All right, so now that we have our Bn, we know that a0 and an are 0 because the function that we're starting with was an odd function. Let's go ahead and put the expansion together. Okay. And so Fourier series expansion, f of t is equal to, we know a0, an are equal to 0. So let's plug in values for n here. Okay. Okay, so for n is equal to 1. Okay. And so for n is equal to 1 here, we know that cosine of n pi is equal to 0. Okay, so our first, or not 0, sorry. Cosine of n pi is equal to minus 1. Okay, so our first term of this expansion is 2 over pi, because the minus signs are going to cancel out. Sine of pi t for n is equal to 2. Cosine of 2 pi equal to positive 1. Okay. And so we have a minus 1 over pi. Sine of 2 pi t. Okay. And I'll do one more. N is equal to 3. Cosine of 3 pi equal to minus 1. That's going to be positive 2 over 3 pi. Sine 3 pi t. Of course, this continues on to Right, so definitely make use of this, and I want to make sure I skipped a little bit of stuff just because I wanted to get through this in case, you know, you wanted to work on the homework over the weekend. But make use of this, the fact that, you know, for even and odd functions, you can save yourself a lot of trouble by, you know, neglecting these coefficients, okay? Okay, any final questions on this today? Okay, all right, so that's all we got time for today. I think we have maybe about 30 minutes of Fourier left, and so we'll finish that up on Tuesday. Homework 5, the deadline for that can be pushed back, and so it's gonna be pushed back to next Friday, just to give you guys a couple more days to do it, because we're finishing up some stuff on Tuesday. And then from there, we'll move on to the next topic, which is Fourier transforms. All right, so thank you guys for coming today. Hope you guys, hope you guys have a good weekend, and I will see you guys next week. Thanks for calling.